Jacob is a seasoned engineer with years of experience in mathematical modeling, full stack development, and data visualization. He helps develop solutions and deploy scientific applications to high performance compute environments. Jacob today is joined by some folks who are going to help him answer questions and be available in the Q&A space. First, we have Dr. Chris Rakakis, our Director of Modeling and Simulation at Julia Computing and the lead developer of JuliaSim. We also have Dr. Harris Organtidis, one of the JuliaSim software engineers. And we also have Sebastian Macluta-Campano, who is joining us as part of the JuliaSim team as well. Now, during today's presentation, if you have questions, feel free to enter them in the Q&A dialogue. We'll answer them at the end of the session, or as one of the team members who's joined can do it. Now I'll pass things over to Jacob and let us get started.
Thank you, Misha. And thanks everyone for joining so we can talk about JuliaHub and JuliaSim Model Optimizer. So let's have a little outline for the day. We're going to briefly talk about why Julia and follow that up with a why JuliaSim. Specifically, we're going to talk about the JuliaSim Model Optimizer. We're going to look into its various model calibration techniques, and we're also going to look at quantified uncertainty. And all of this will be demonstrated with some examples at the end on the JuliaHub platform. And the first example that we'll do is we'll take a look at constructing and calibrating a Chua circuit model. And second, we'll calibrate a building model. So that's the outline for today. Let's dive in. So why Julia? Well, Julia is purpose-built for technical computing. It's expressive, performant, parallelizable, and more. And all of these attributes have made Julia the 5th most loved programming language according to Stack Overflow's developer survey. So you can see this love is obvious when you see how quickly the ecosystem is growing. So there's a fast number of packages being built, really rounding out this Julia ecosystem. And crucially, Julia solves the two-language problem, wherein research or proof of concept code is typically written in something which is expressive but slow. And then production code is rewritten in a language which is faster but suboptimal for developer efficiency. And Julia addresses this problem by making it easy to express your ideas in code while also achieving excellent performance. And these graphs help illustrate that idea, the gains that you can achieve when you're going through this process once through with Julia instead of rewriting code to achieve the performance that you need. And if we take Julia's differential equations package as a prime example of solving this problem, we see that Julia meets or beats the performance of compiled languages, even though it's just as easy to write as many of the widely used interpreted languages. So it's something that you have a modern language, very nice to use, but you're really getting those performance benefits. And that is a pretty solid case for why Julia. But why JuliaSim? And for starters, the place where we have to start is in JuliaSim's foundation, which is JuliaHub. And that is the best place to build and scale your Julia projects. It's really bringing the power of supercomputing to individuals, to small teams, to large industrial teams. Additionally, JuliaSim is a modern SciML suite with many different modules included. Today's going to focus on the Model Optimizer, and the Model Optimizer is a package and methodology to perform model calibration, perform analysis, do all this in a high performance environment and in a user-friendly manner. So we're going to look at the robust and automated framework that it provides so we can scale large and complex models. So JuliaSim for model calibration. This is a brief introduction into what problem we're going to solve. And this is the process which helps us convert models and data into calibrated systems with quantified uncertainty. But nonlinear model calibration is a difficult problem in general, and there's several challenges which are included, and you can see them here. This includes hitting local minima. It can be difficult to run these techniques in distributed fashions, so you're oftentimes constrained to serial implementations, which is costly from many aspects. And then also some model parameters may be unidentifiable from the data. So these are all of the various challenges which are introduced in this space. And what I want to do over the next couple of slides is walk through how JuliaSim Model Optimizer addresses these. So to address the first challenge, how do we avoid local optima? Well, we can leverage specialized methods from Model Optimizer to avoid local optima. And there are many calibration methods available. You see some of them here. All of this is available in the suite, which is Model Optimizer, and which one you choose is going to depend on the particular problem at hand. To address the second challenge of how do you do effective parallelism on the particular strategy that you're employing? So how do you leverage large-scale cloud compute systems to solve these problems? And the proper strategy selection plays a big role here. So you can enable parallelism with certain strategies that you wish to employ, such as multiple shooting being one example of this, where if that is an effective strategy, then it helps you kind of break out of this serial execution. So we have many methods available to our disposal, some more amenable to distributed compute and cloud computing systems. So that's the challenge 1 and 2 addressed. And we mentioned a third, which is that model parameters can be unidentifiable from data. So how do you quantify the uncertainty in the fit? And this is where we introduce the concept of virtual populations. So virtual populations, we're going to define some terms here. Virtual populations are sets of parameters which sufficiently fit all trials, all observations. So a trial here is a different variation of a model which can be run. So it describes an experiment. This is a data observation. We can have collection of trials. So we can have many trials, and with this collection, we can define multi-simulation optimization problems. And this is, this is the problem. Before we really get into seeing this in action on the platform, we need to discuss some different modeling paradigms. So how we actually create these simulations and have something that we can apply these model optimizer techniques to. So we're going to look at a couple different modeling paradigms, and we're going to start with causal modeling, wherein we describe the causal mechanisms of a system. And the way that this works is that we provide clear rules for the interactions between functional blocks. And we can make an analogy to imperative programming here, where we're really focused and we're worried about the flow of computation. So that is causal modeling. It leads us nicely into another approach, acausal modeling, wherein we describe the behavior and the properties of model components. And then models are built up out of these components, so out of the composition of these components. And what happens is the overall dynamics of the model fall out of the cumulative behavior of that composition. So we kind of used the imperative programming analogy. Here, let's employ the declarative programming analogy. So we only want to worry about the connections and the relationships between these functional blocks. We don't want to frame the problem particularly in terms of the flow of computation that has to happen. Instead, we want to think more about individual components and their relationships to one another. And that's what we're going to use here. We're going to use the acausal modeling system because it offers some advantages. First and foremost is we can be expressive. So we can think like scientists and engineers. and we're not limited to framing the problem only in terms of how to compute the results. We can be concise, so we can build large-scale models by connecting well-tested components, and then reusable in that we can bring these well-tested components and entire component models with us to build new systems. So all of this is why we want to use an A-causal modeling framework. Today, you're going to see an example of how we do this with Julia's modeling toolkit, which is the A-causal modeling framework, and it's going to allow us to be expressive and concise when we write our differential equation models. And it's also going to enable us to reuse this model so we can automatically rearrange equations for better stability. We're going to get a couple of other extra perks here. We're going to get optimal code by default. So without having to worry about the most optimal way to compute these things, we just worry about the mechanics, and then we get that optimal code for free. And this code is also going to be parallelizable by default. So these are all some nice benefits of modeling toolkit, and that's what we're going to use for our examples. We're also going to use some components from the modeling toolkit standard library. So speaking of reusability, we're going to leverage some pre-built components from the standard library. And this is going to help us just kind of dive directly into the engineering and not focus as much on the math, the programming, building all of these things up from scratch. So this is exactly the use case, the intended purpose of this model library. We're going to leverage it. Okay, so now we have everything we need for the first example. In the first example, we're going to look at a Chua circuit model. This is a simple electrical circuit that exhibits chaotic behavior. So a couple nice things about this: it's easy to construct, and it's kind of a classic real world example of what a chaotic system can look like. In order to get this chaotic behavior, we need to satisfy a couple of requirements. If you look at the diagram here, we need at least one nonlinear element, and that's what NR stands for. That's going to be our nonlinear resistor. We need at least one locally active resistor, also NR in the diagram. And then we need at least 3 energy storage elements. So that's where the capacitors C1 and C2 and the inductor L come in. So this is the diagram that we are going to be building. We're going to use modeling toolkit and the modeling toolkit standard library, and we're going to be building this on JuliaHub with the JuliaSim IDE. And so now you can see my IDE here. So this is our first look at building a model with Julia code and modeling toolkit. So the first thing that we're going to do in this is we're going to load some packages. JuliaSim Model Optimizer being the first package. You can see here how we access these standard library components. So we're going to be pulling from the electrical module, and this is one particular component from that electrical module that we're going to use. We also pull in the ordinary differential equations package, as well as modeling toolkit from the SciML ecosystem. And then we have data frames, statistics, some various packages here to handle our experimental data, and stats plots, which is going to come in handy. So let me just load these packages. And now we can start to define the model components that are not readily available in the standard library. So first, we just need a parameter for time, and then we can build out our nonlinear resistor. So this is the code representation of exactly what was shown in the diagram. As I said, you can see that we are using some components from the electrical module of the modeling toolkit standard library. And then it's pretty straightforward for us to describe the various equations that we want this nonlinear resistor to exhibit its behavior describing. So we have a couple nested if-else statements here that basically employ different equations based upon different conditions of the nonlinear resistor. And what we end up with what we return from this function here is an ordinary differential equation system, ODE system here. So this is going to help us create that component. I'll just run this. Okay. So now that was the only component that we needed to build ourselves. Now we can actually create the model components using the nonlinear resistor that we just wrote, and then also using some of the standard library components. So inductor, resistor, conductor, capacitor, and ground are all from the electrical module of the standard library. Calling these, using these is very easy. We can create the model components with the same labels that we saw in the diagram by executing this code block here. And once we have each of these elements, we can start defining the relationships between these components. And that's what you see here in the connect statements. So what I talked about, not necessarily having to worry about writing the optimal code, but instead just describing the relationships between each of the components. This is what you see here. So we can connect the inductor to the ground, the nonlinear resistor to the ground, the capacitor to the ground. We can do all of this with connect statements. And at the end, we feed all of these connections, so all of these equations, along with the systems that are made up of the system. We can create our ODE system, put it in a variable here called model, and that is going to give us kind of everything needed, right? But we didn't pay close attention at all to making sure this runs in an optimal way. Well, that's where structural simplify is a very handy tool. We can pass our model into this structural simplify call, and it's maybe useful just to look up the help here really quickly for structural simplify, just to kind of get an idea of what's going to happen. But it's going to simplify the algebraic equations of the system. So wherever possible, it's going to not make redundant calls. It's going to find the fastest method to solve this model for us. And so if we just call this method on our model and store that result in a variable, then we get that optimal code for free. So once we have that optimal version of the model, we can create our ODE problem, run it over a particular time span, and we're going to give us some instructions to save at certain times. This is mostly for plotting later. And then we can solve this problem. So that's done. And now we have everything that we need to start defining our inverse problem. So the first step to defining our inverse problem typically is we would load experimental data. So typically you might see something here like using the CSV package, read in a file where I had all of my experiment data saved, and now I want to tie this data back to a model, right? In this example, I'm just going to use the solution that I got directly above from calling solve on our problem. So let's just create a data frame here. We'll run we'll run this line, get some data, and then since we already have our model defined above, we have everything that we need to define a trial. So a trial is our model plus our data. And that's as easy as this. So here we're going to pass in the data, pass in our system, tell it what time to run over. And then there's just, now that we have a trial, we can create the inverse problem. I'm just going to run this block as I kind of talk through the next section. So when we create an inverse problem, what we're doing is we're specifying the parameters that we want to optimize, and we're also specifying the search space that we want to look for. So that's what you see here. We're passing a collection of trials. Granted, here it's a single trial in this collection, but it's still a collection. We're going to pass our model, and then this is the search space. So you can see here the model parameter, the lower and the upper bound for each. So what this is going to do is it's going to find the model parameters in the system, and it's going to find the parameters which cause the model to be a sufficiently good fit to all data here being the collection of trials that we passed. And since that's done, we'll move on to the next block here, which is the virtual population. So it's the plausible population of optimal points. So creating this virtual population is as easy as feeding in the inverse problem, passing an optimization algorithm. So in this case, we're using the stochastic global optimization algorithm. We're going to do a max iteration of 100 here. 5,000 is a much more kind of realistic number to use, but just for the sake of the example, we're keeping this pretty low. And when we create this, we can see the data frame that was produced on the right. So if we just scroll up a bit, and we take a look here at our two capacitors that we defined, for instance. So when we defined C1 and C2, we passed in values for C. And you can see here in the results of the virtual population, C1 and C2, this is model parameter C. For C1, we passed in 10. You can see many of these values are right around 10. That's a relatively good sign that what we're doing is we're getting close to that value. Same thing for C2, that's 100. So we can see many of these are right around 100. So that's kind of an eyeball test. Let's run this visualization section here just to get a more clear way to see these results. Excuse me. First way that we're going to do this is just load in some parameters to make this easy. We're going to create a single image that's a layout of 3 images, and for each one we're going to use a smooth density plot to show the virtual population. And then since we know the true value, we're going to plot that to use for comparison. Okay, so plots generated, and this is for each of the 3 that we searched for, R, C1, C2. We can see the dashed line is the true value, and the blue line is the estimate. So we can see that with a low number of iterations, we're still capturing these true values pretty well in the virtual populations. And we did this, so let's kind of review. We did this by first creating the model with Modeling Toolkit, the A causal modeling framework. We really only had to create one component from scratch. And even that, we're able to leverage the one port component from the electrical module there. So we connected all of our model components. We got some optimized code, and then we used that to generate some synthetic data and create this inverse problem. And then directly from there, we could create this virtual population. So this is kind of the whirlwind overview of what it may look like, a model optimizer workflow. I want to just switch back to the presentation now. Okay, perfect. And that was the first example that was promised, right? So we looked at a Chua circuit example. Now let's take another look at an example of a building model. So this building model is an 81-room building. It's 9 by 3 by 3. It's cooled by circulating water. And what we're actually going to see here in these graphs is 1 week of real meteorological data. So it starts on the middle of July in Phoenix, Arizona. And I'll hit play there. Perfect. So you can see that the image on the left of the building it correlates to the vertical line that's moving across the plots on the right. And on the top, we get the room temperature of each of the, a room here. And then on the bottom, you see the ambient temperature throughout the day. So there are 7 peaks and valleys. on the bottom, and that correlates to the sunrise over a week, sunrise and some fall of this data. So we can see how the time of day and the heat from the sun is affecting the ambient temperature, excuse me, and also the room temperature. And then the building has an animation to connect the temperature of each room with a color so that we can distinguish that nicely. So how might we construct a model like this with an acausal modeling framework like Modeling Toolkit? Well, after we load some packages, just like we did before, we're going to need Modeling Toolkit. We're going to need ordinary differential equations, probably some things to handle some experimental data like data frames and CSV, data interpolations package. We're also going to pull in something which is a package of components that we've developed to break down this problem into smaller portions, very similar to a standard library. So after we've done that and we load our meteorological data and we slice all that data, get everything kind of ready, we can start to set some structural parameters of the model and for the building. So you don't see it here, but we do set some initial temperatures for the building, and in the model, the temperatures are measured in Kelvin. It's important to note because we'll end up converting those later, but we just kind of set the stage, set all the initial conditions, get everything ready. And then once we have that, we can do some component setup. And that's what you're seeing here is, very similar to how we would just pull in a capacitor, an inductor, a ground source. We can pull in these interpolated sources, constant sources, step sources. We have a function to create a hex fan there. We can create each one of these components, and we can actually create many of them in one go. That's what you're seeing there with the array syntax. And then, just like before, instead of writing this massive model by hand, which comes out to be over 17,000 equations, instead we can focus purely on the relationships between these components. So this model is built up by the composition of each one of these components that you saw before. And the overall dynamics of this building model, they fall out of the cumulative behavior of that composition. So it's kind of all of the individual components, of all their dynamics, and of all the connections that we declare here. You can get the dynamics of the full model out of that. And what would be 17,000 equations, if you were maybe going to write this by hand or write everything out explicitly, we'll see that we can drastically reduce that number later on. And again, we only worry about the connections, the relationships between each one of these things. And this is actually even done in a nice and concise, fast way, because we're able to do this in a for loop. So we're going to go over each room, set up these equations, these connections for every room in the building without having to code this by hand. And the output is an ODE system. And with this, let's now go over back into the IDE. Great. Okay, and let's take a look at how we're going to do this. We're going to cut a corner here. I'm going to use something pre-built instead of defining all these, but you just got a good idea of what it may look like to do this all from scratch. So first, we're going to load in the building model library. We're going to load in JuliaSim Model Optimizer. Everything else very similar to what we did before. We are going to deal with some unit conversion, Celsius to Kelvin. So we'll need that as well. So let's run this. Okay, great. So instead of building the model from scratch, we are going to use this initialize model function call, which comes out of the building library package. So we'll give this a moment to finish running. And we can see the output here. So 2,619 equations is a massive reduction from the 17,000 equations that we started with. And that's because the model that we get out of this call, it has already run all of the various reduction algorithms to get this structurally and algebraically simplified. So we have a nice lean model to work with. What we want to do here is define some model parameters. And again, this is where the unit conversion package comes in nicely, because seconds to hours, later on Celsius to Kelvin, this becomes just very nice and easy, and there's really little room for developer error here. So let's just define these model parameters. And once that's done, we can define the inverse problem. So we're going to follow the same 3 steps as we did last time. We're going to load in some data, we're going to create some trials, and then we can define our inverse problem. So first, looking at the data, this is much more representative of what you would normally see. As I said before, this is going to be loaded in from CSV read. So I have some building data. I've loaded it onto JuliaHub, and now I want to access that. We're just going to simply read that in. I'm just going to go ahead and run this cell while I walk through everything. So now that I have my data and my model defined, it's time to create the collection of trials. In this case, it's one where I feed in the data, feed in the model, give it a time span, and then here, optionally, I specify an algorithm as well. And then moving down to the inverse problem. Again, we want to specify the parameters that we want to optimize and the search space that we want to look for. So passing in our collection of trials, passing in our model, we only, in addition to that, we only need to provide the search space. So for each of these model parameters, provide a lower and upper bound in the model. These temperatures are represented in Kelvin, so that's why you see the values that you do here. And create this inverse problem. And once we do that, we have everything that we need to calibrate this model. So just take a second for that to finish running. But notice here that we're going to call calibrate, which comes from JuliaSim Model Optimizer. We're going to provide this input, this inverse problem. And we're going to provide this algorithm, which in this case is this spline collocate, where we provide a max number of iterations, we provide a solver, and we call calibrate on this inverse problem with this algorithm. Once that's done, all we have to do is convert the results from Celsius to, from Kelvin to Celsius. And then we will have the parameter estimation for this model. So should be completing soon. Just while I'm waiting for that to complete, I'm just checking some Q&A. And there's a question from Marcel. Says, I almost agree, but if the number of actual point is really limited, this is just a curve fit. It looks like we're responding in the chat. I don't know if Chris, you want to come off mute and address that? Looks like he's going to address it in chat.
Yeah, so I just want to clarify that, all these methods that we're showing here, they are large scale, they're methods that are designed for large scale simulations to fit to data, right? It's a form of curve fitting that is made for robustness to nonlinear behavior. So, in the questions, there was questions about, how do you do this with a chaotic system? These questions are well founded, right? Because, for example, chaotic system, you have O of one error in your simulation if you simulate it for multiple Lyapunov times. But the techniques that we're demonstrating here are robust to those kinds of behaviors, right? They make use of things like multiple shooting, and they make use of things like, collocation, to be able to be fitting in the derivative space in a way that does not require, that does not have this compounding of errors. And so, it's a good question, because, if you naively run, say, if you slap a ODE solver into BFGS and then, just directly hit, fit, and then you hope and pray, chaotic system is an example where such a technique would fail. And that is exactly why, it's one of our demonstrations here, just to showcase that, the techniques that we're using have this kind of robustness for these kinds of systems.
Yeah, thank you for that clarification, Chris. There's also another question in the chat of how many machines simultaneously does it run on? What controls how many resources are available for a user? And I think that this is a good time to also show that because we're running this on JuliaHub, all of this is very nicely handled for us in a kind of abstracted away, so that we can worry mostly about the scientific problem at hand and scale this with relatively or no effort here. So let me just really quickly switch over. So this is JuliaHub.com, and you can see here that I have some different applications available to me. Each one of these applications can be configured to run on a different number of resources. So I can choose the architecture, I can choose the number of virtual CPUs, the amount of memory, I can choose how long to run it for. And so this is how I might do it from an interactive standpoint. And from within the IDE here, which is running on JuliaHub, I also have the ability to kick off batch jobs and control the resources that are going to be used to run that. So let's cancel that for now. So what I did is I opened up the JuliaHub extension here in the JuliaSim IDE. This is VS Code interface here. So let's just say, for instance, that I want to run this building model. If I click to use the current file, which is the one that I have open, that I'm editing, it recognizes that. I can also choose to provide a bundle directory. And so if I select, let's choose the one that so this is where the project toml and the manifest toml lie. And so I can just provide this as the bundle directory. It's also going to know about the data directory, which is subdir here. And then I can start a distributed job. And I can start rather any job. It can be distributed or it can be single process. Let's just say that I want to run a distributed job on CPUs. And I want this job to have a certain number of vCPUs and memory. I just specify all of that right here. Let's knock these down. And I provide a number of nodes. So I show how many machines of this configuration I want to start up for this job. And then I can limit it just in case I don't want it to run longer than some amount of time. I can limit that. And I can provide a name, and I can submit that job all from right here within the IDE. So in terms of how many machines does it run on, what controls that, really the user has full control on submitting batch jobs, exactly what type of machine they want these to run on. And then we also get right from the JuliaHub website, you get a nice interface to monitor your interactive jobs, which is what you're seeing here, as well as batch jobs that you submit. So you can get some nice logging information and results directly from JuliaHub's homepage instead of from having to log into the IDE. And as I was walking through that explanation, we can see here that we got the results from the calibration, and we see here we get also the unit conversion from Kelvin to Celsius. So that kind of brings the building model example to a conclusion. And I'm just seeing some other questions in the chat. So does it have support for MPI for problems which don't fit on a single machine? There's two questions here, so I'll just, I will address the first, and that's yes. So there are already examples on the platform which are using MPI because that makes sense to do for these problems. MPI is certainly an option. I do just also want to point out that for Modeling Toolkit and the wider SciML ecosystem, distributed compute is also something that you get by default from a lot of these tools. So it's meant to be modular in design such that you get the nice causal modeling framework, you get a lot of various solvers and optimization algorithms and so forth, and all of it's also nice. It's a nice common interface which is meant to be easy to scale to these distributed type of jobs. So MPI is an option, and then oftentimes it's even simpler. Running an ensemble of simulations is really just as easy as configuring the number of nodes with the particular machine type that you want, and hitting submit and kind of letting JuliaHub take care of the rest. So you get to really not worry so much about the infrastructure side of things and focus on the engineering problem at hand.
Yeah, and let me chime in for a little bit of extra there. What is used with JuliaHub is a form of distributed computing. It's not exactly MPI, but it's in a functional sense, it's very similar to MPI, and so yeah. So these algorithms are made to work for more machines, and internally inside of the algorithms, they're already set up to make use of whatever compute is available. And so what you need to do in order to make use of that is you just need to run a JuliaHub job that has multiple machines, right? So you can tell JuliaHub to spawn a job with 1,500 cores, and then the internal algorithms of JuliaSim's Model Optimizer will make use of that. So if you then say, make a virtual population with 10,000 points in the population, the algorithms will know to then make use of the 1,000 cores that you spawned, right? So it's not exactly MPI, but it is a very similar thing, and it will make use of many different machines or vCPUs across the cloud system. And can you batch job programmatically from a YAML file? You can use the JuliaHub API for doing that. Something very similar to such a YAML file. I would point to some of the webinars on using JuliaHub to go into more details on that.
Yeah, thanks for adding that, Chris. So I also see a question about a graphical UI, and in parentheses, flow sheeting, which I'm not sure if I've heard that term used as much, but I assume that the question is really, when we're making these connections between these model components, is there a graphical UI to do the same, right? This is something you might see in a modeling tool. And the answer is that in the future, yes. So this is absolutely something that we understand many users may want. And also, as you may expect, the goal would be to provide a graphical interface to form these connections. So pull in components from ready-built libraries, connect them with a GUI, and then still get this same code output that you see. And the reason for that is we don't want to take away the flexibility the code output provides, right? So in the future, when the GUI is available, you'll also still have access to the underlying, human readable code. And that way, if and when you kind of develop more comfort and maybe faster to do some things directly in the code, you're still going to have that available to you. And before I move on, I just want to kind of pause, make sure that I leave room for anyone to add onto that point there.
Yeah, so I answered in the chat. Basically, the GUI right now is in development. We are building a flow map GUI for modeling toolkit, though it's not quite ready for outside use yet. And so, stay tuned for future updates from Julia Computing, and we'll definitely be talking about this in the near future.
Absolutely. Thank you, Chris. Okay, I see one more question in the chat. It says, optimization with units within models possible. And then there's a dimensional analysis portion here. Chris, would you like to chime in on this, or Harris or Sebastian?
Yeah, so I'll say that, I mean, the units approach is in progress, so that should actually be rather close to completed. Modeling Toolkit does have a way to be able to specify what variables are supposed to have what units, and then it performs a unit verification. So that way you can ensure the dimensional analysis is all correct within a model. This has not been propagated all the way up to the optimization tools yet, though this is something that we are looking into, and it should be something that should be there in a future release.
Awesome, thank you. So that brings a close to the demonstration portion. And another question just popped up. What is the approach for empirical formulas? Asked again by Mr. Rosenfeldner. And yeah, I'd like to invite again Harris, Sebastian, Chris, anyone to join in on that, since we have a few minutes left.
I'm not entirely sure that I understand the question as written. So if you'd like to re-ask it in another way, maybe we can help you out here. Or if you have deeper questions, I think that we can follow up through email, and that might be an easier way to have a deeper discussion.
Yes, good point. Yeah, there's many places where you can reach out with questions. Attempted clarification: empirical formulas may have problems with units. So yeah, without kind of knowing exactly what issues may occur here, I will just kind of note I've worked with the Unitful package in the past, and it is very nice interface where, again, it kind of takes a lot of the potential pitfalls, potential bugs that may be implemented by developers, kind of takes that off your plate in a lot of ways, because it's a very kind of nice and clean syntax where a lot of that unit conversion is done for you, right? So your model can do what it does, and then at the end you can get the particular results that you wish. I see that Sebastian has raised his hand.
Yeah, I wanted to ask if by the empirical formulas with units you mean formulas where you have some constants that are obtained from various experimental situations, and you don't necessarily have all the units put into place in the equations. Like, you know that you have some constants that have some particular values, but the units are implicit. Is this what you're referring to, or is there something different?
Yes, so it seems like that is.
Yeah, so in that case, if you have the units implicit, I think it would be best to just add the units word. Here it depends more precisely on the problem at hand to see if we can handle it via unitful by adding multiplying with the required units, or just to strip the units entirely and see what other approaches that we can take.
Yeah, one nice thing might be to offer just a little bit of information, just in case folks aren't aware. So if you visit the Julia Lang website, that's julialang.org, you're also going to have access to all of the various community forums. So there's on almost every place you can imagine: Slack, Discourse, any other forum site. As I mentioned, Julia is a well-loved programming language. We at Julia Computing are very active on in many of these places as well. And so maybe if you do have any particular questions, filing something on GitHub on one of these forums might be the way to kind of spark some spirited conversation around that.
Sorry about that, Jacob. Thank you very much for your presentation. Chris, Harris, Sebastian, thank you very much for adding some clarification. And of course, thanks to everybody who joined us today for the webinar. I know some of you may still have questions. You are welcome to reach out to us. info@juliacomputing.com is a good catch-all for us, as well as you can go to our website and submit a contact us form. As promised, we will be sending out a follow-up email that includes a recording of the webinar so you can review it. And we look forward to seeing you at other upcoming webinars. Thanks very much, everyone, for attending today.
Thank you. Bye-bye.